Hi everyone, my name is Daifu Liam. Welcome to my final project presentation for the CSCI E-89B course, Natural Language Processing for the Master of Data Science at Harvard University, Harvard Extension School. My work focuses on building and evaluating deep learning models that auto-tag short medical questions with multiple relevant labels. I experimented with 5 neural architectures, from lightweight CNNs and RNNs to transformer-based models. And then I compared them on the same clean dataset with consistent evaluation. So in real settings, what I see is that medical platforms receive thousands of short and structured questions. So I find out that assigning consistent tags helps triage, retrieval, and downstream analytics. Manual labeling doesn't scale, especially with hundreds of possible topics. So I wanted to build a pipeline that learns how to assign multiple tags per question, even when labels are sparse and imbalanced, unfortunately. So my task is multi-label classification. A single medical question can map to one or several tags at the same time. However, my dataset is long-tailed, highly imbalanced, and noisy, reflecting the real context. So I define my success by depending on handling these challenges while producing well-calibrated predictions. So now let's look at the data, basically. The raw data set contains about 47,000 rows. So after I remove 25,000 duplicate questions, I would have about 22.5 thousand unique text remains. But I also need to filter data to retain the questions having the text occurrences of over 100. So after exploding multiple tags of each questions into multiple rows, I would have about 112,000 rows left. Therefore, the unique text kept would be 279. But I would still need to apply a predefined now whitelist for all of the rows. So it would drop down to 86,000. Therefore, I would have unique text kept by 217. And I also need to apply the normalization on the data as well. But still, after normalization, I have left 86,000. The dataset has a classic long tail shape, is what you can see. A few labels appear frequently, while most labels occur fewer than 10 times. Even after filtering out text with fewer than 5 occurrences, the majority of labels remain sparse. This makes stratified splitting critical. So this is one of the reasons why I put a filter to retain those tags with occurrence more than 100. My pipeline standardizes the tag format, converts everything into clean Python lists, removes empty rows, and applies a rare label filter. I then generate the multi-hot label matrix using multi-label binarizer. Only the training split is ever used to fit text vectorizer or tokenizer, which avoids leakage. Because simple random splitting loses minority labels, I have to decide to rely on iterative multi-label stratification. The final splits are roughly 86K training rows after exploding tags, like I mentioned earlier. Therefore, what's left would be the 222 validation rows and 568 test rows. This ensures more stable metrics, especially AUC. Preprocessing focuses on label consistency and leakage safe splitting. The tag column is parsed into a clean list format, where labels are removed to reduce stream sparsity. Text is tokenized with a 128 token cap. Multi-label stratified splitting preserves label co-occurrence patterns across splits, which is important when labels are rare. So let's talk about the model. I implemented 5 models. V2.4, which is a DistilBERT mean pooling with leading hat, and this is an unmasked mean pooling. V3.2 is quite the same, but this is a masked mean pooling with deeper NLP hat. For the V4.2, it is by LSTM with learned embeddings and pool representation plus the NLP hat. V5.2 and V6.2 are quite the same in terms of having the GRU and LSTM respectively, with the same attention plus, mean pooling and MLP hat. So all of these 5 models have a common setup with binary relevance, signal outputs, global threshold tuning, and each model uses the same dataset for sure, as well as the same evaluation logic and consistent preprocessing. So all models predict 217 independent probabilities with sigmoid, treating the task as multi-label binary relevance. A global threshold is selected based on the validation set to convert probabilities into predicted text sets. A major comparison axis is parameter scale. DistilBERT models have around 66 million parameters and leverage pre-trained training representations. The RNN models are much smaller, around 4 to 5 million parameters only. And they learn representations from scratch via embeddings and sequence modeling. This difference affects ranking quality, calibration, and sensitivity to threshold choice. My training objective is binary cross-entropy with losses across 217 labels. Post-weight addresses imbalance by increasing the parity for missed positives. For the PyTorch models, mixed precision improves training efficiency. Early stopping relies on validation micro ROC and AUC, since it is threshold independent and more stable than strict accuracy metrics in multi-label settings. So here's my evaluation strategies. The evaluation gives both ranking and selection views. Micro ROC AUC measures how well the model ranks true labels above false labels across the entire label space. Threshold-based metrics evaluate the final predict text set at a chosen global threshold. Subset accuracy is strict and typically low in multi-label problems. Top K accuracy is included to reflect tag recommendation performance. So let's compare the models. This table summarizes the architecture and training setup for all 5 model versions. As you see, the first 2 models, version 2.4 and version 3.2, are DistilBERT-based. Both use the DistilBERT tokenizer with a maximum length of 128. The key difference is pooling and decision logic. Version 2.4 applies simple mean pooling and uses a fixed global threshold of 0.5, while the version 3.2 uses masked mean pooling, a deeper classifier hat, and a validation tool threshold of 0.75, which improves the calibration. The remaining models use lightweight recurrent architectures with custom tokenization. Versions 4.2, 5.2, and 6.2 all use regex tokenization a capped vocabulary of about 30,000, and trainable 200-dimensional embeddings. Version 4.2 uses a bi-LSTM with pool representation, while version 5.2 and version 6.2 add learn token level attention on top of GRU and LCM encoders. A major contrast is scale. The DistilBERT models have about 66 million parameters, while the current models are under 5 million. Despite this gap, all models use the same loss function, binary cost entropy with per label positive weighting, and the same AMW optimizer with warm-up, decay, and mixed precision. So overall, my setup allows a fair comparison between high-capacity pre-trained encoders and efficient recurrent alternatives, with differences in performance driven mainly by representation quality and threshold calibration rather than optimization choices. So let's look at the matrix. The strongest micro F1 comes from version 3.2. The DistilBERT model with a deeper MLP head at a tune threshold of 0.75. Version 2.4 shows excellent AUC but lower micro F1 at a fixed threshold of 0.5, indicating threshold sensitivity. Among the RNNs, version 4.2 and version 6.2 are close in F1 and AUC, while version 5.2 is the weakest in F1 under the global threshold setting. Furthermore, let's look at the top K retrieval behavior. Accuracy at 1 ranges roughly 0.3 to 0.39. Accuracy at K is high for DistilBERT models and drops for RNN models. The best accuracy at K from version 2.4 at about 0.95. The top K metrics show that correct labels are often ranked near the top, even when exact selection is imperfect. The version 2.4 has very strong accuracy at K, suggesting that mean pool DistilBERT ranks relevant text well. RNN models have lower accuracy at K, which aligns with their weaker ranking performance and lower AUC compared to the DistilBERT. So for the training processes, here's my training dynamics and early stopping. DistilBERT version 2.4 converges fast and stabilizes with high AUC by early epochs. DistilBERT version 3.2 shows longer warm-up than rapid AUC improvement. RNN models improve gradually but plateau earlier on AUC. Training curves indicate that pre-trained encoders reach strong ranking performance quickly, while RNN models require more epochs to learn representation from scratch. Early stopping based on validation AUC prevents overfitting and reduces runtime. The plateau patterns also suggest that my model capacity alone is not sufficient to overcome long-term sparsity without improved calibration strategies. So these 5 charts show per label precision recall curves for the most frequent medical texts. Recall is on the x-axis, precision is on the y-axis. Curves that stay higher indicate better performance, and the AP values summarize each curve across thresholds. I use these plots to see which medical concepts each model handles well and where ranking breaks down, even when micro AUC looks strong. In the 2.4, pregnancy and pain are clearly the strongest label, while period and blood are moderate. Sexual and intercourse drop quickly as recall increases, showing confusion for more sensitive or context-dependent topics. In V3.2, the curves are more balanced. Pregnancy and pain remain strong, and period improves noticeably, suggesting a better separation of overlapping symptom language. Fewer curves collapse early, so ranking is more stable overall. In version 4.2, most AP values decline. Precision drops early as recall increases, which signals weaker calibration and ranking, likely due to added model complexity on limited data. Version 5.2 is the weakest set. Precision falls sharply for most labels, especially sexual and intercourse, indicating difficulty separating correlated tags. Version 6.2 recovers some performance. Pregnancies and blood improve, as sexual stabilize compared with version 5.2, though precision still degrades at very high recall. Overall, pregnancy and pain are consistently the easiest labels, while sexual and intercourse remain challenging. These plots show why micro AUC alone is not sufficient and why per-label analysis is critical for reliable inference and thresholding. So these 5 heat maps show top 1 confusion matrices for the most frequent labels. One per model version, and each row is true label. Each column is the predicted top label, and brighter diagonal cells mean correct top 1 predictions. Across all versions, pregnancies is consistently the strongest label. It appears clearly on the diagonal in every block, which matches its high frequency and distinctive language. Disease, test, surgery, and stomach also relatively stable diagonal behavior, especially in the transformer-based model. The main failure pattern is confusion among semantically related labels. Pain, period, blurred, and pressure often overlap, which reflects how short questions frequently mention multiple symptoms at once. Sexual and intercourse are also confused with each other across all models, indicating ambiguous phrasing rather than a modeling bug. Comparing models, the DistilBERT versions show the cleanest diagonals and fewer off-diagonal errors, meaning better separation when selecting a single best label. The recurrent models spread probability mass more broadly, which helps recall but hurts top 1 precision. The lighter Conv 1D model performs reasonably but shows more confusion for overlapping symptom labels. Overall, these plots confirm that most errors are clinically reasonable confusions, not random mistakes, but they reinforce the idea that these models are better suited for top K recommendation than strict single label prediction. So here are the example inference. A sample question such as, does SOMA show up on a drug urinalysis? Produces text like drug, test, overdose, pregnancy, and depression, but only drug is the highest ranking prediction that matches with the true tag drug. The results suggest that pre-trained transformer encoders provide the best ranking and selection performance overall. However, accuracy at 1 is strongest for the bio-LSTM variant in these logs, indicating that smaller models can still provide good top prediction quality. Threshold selection is the main bottleneck, especially for RNN models, where global thresholds yield high recall but lower precision. Several choices clearly improve results, including masked mean pooling and threshold tuning. The major limitation for me is that a single global threshold cannot handle label-specific base rates. Strict exact match metrics remain low because even one missing or extra text makes a sample incorrect. A stronger calibration strategy is needed for stable precision recall balance. My projects reinforce that metric selection shapes conclusions. Micro AUC provides a stable picture of ranking quality, while subset accuracy is overly harsh. Threshold is the key challenge in multiple label classification with imbalance. Even small architectural changes in the classification head can shift calibration and change F1 substantially. My next improvements should focus on calibration and decision rules rather than only architecture. Per label, thresholds can address a different label frequency. Calibration methods can improve probability and interpretability. Label grouping can reduce correlated overprediction. A larger validation set would stabilize threshold tuning. Domain-specific pre-trained models may further improve representation quality. My project shows that multi-label tagging for medical questions is achievable with strong ranking performance, especially using pre-trained DistilBERT. The strongest overall F1 comes from version 3.2 with a tuned global threshold. The RNN models are much smaller and still competitive in AUC, but precision remains a challenge under a global threshold. The primary takeaway is that calibration and threshold strategies are central to multi-label success in long-term settings. This is the end of my presentation. Thank you for listening.